Hello guys, welcome to the next tutorial of VREP. In this video tutorial, you will learn all these contents. Firstly, we will look into the object properties of different shapes in VREP. Under this topic, you will learn what is a dynamic and a respondable body. Then you will look into joints and force sensors. Then we will be finally getting familiar with the collector board model. Now let's open VREP. Once you open VREP, you will get a window like this. To add a primitive shape, as you know, select add and then select the corresponding shape you want to do. Let me select a cylinder. Let's give a dimension of 0.2 meter and a height of 0.05 meter. So now I get a cylinder with the dimensions I have entered. Let's learn the characteristics of this model. You know that this shape indicates that it is a pure shape and it is a primitive shape. Double click the cylinder to get seen object properties. You will notice two tabs, shape and common. Select common and then you will see a visibility section in which the camera visibility layer's first column is being checked. Uncheck the column and you will find that the cylinder just becomes invisible. To bring back into the visibility layer, check it again. Under the shape tab, you will see show dynamic properties dialog. Select it and by default you will see that the body is respondable and the body is dynamic has been checked. Let's see what is meant by a dynamic body. To translate, select the item shift and using the mouse translation, as I have to move it along the Z axis, let me select along Z, then click it and drag it a bit. So now it has been translated to a certain height. If you click Start Simulation button, you will see that the body just falls down, just like any natural body. It is because the body is set as dynamic. So if the body is set as dynamic, VREP understand that it has a mass and hence inertia. If you uncheck body is dynamic, then if you start the simulation, you will see that the body remains in the air. It acts as if it has no mass. Now let's see what this body is respondable means. Let's make the body as dynamic and let's uncheck the body is respondable. And now let's start the simulation. You will see that the body just falls down and it does not respond to the ground. So if the body is set as non-respondable, it does not respond to any other collidable or any other materials. Let's invert that change. Now let's learn what is local respondable mask and global respondable mask. Let's add another primitive shape, say a cuboid. Let's give a dimension of 0.2. Now we'll see a cuboid in the scene. Let's translate it a bit away from the cylinder. Now let's run the simulation. And while the simulation is still running, if I shift the cuboid towards the cylinder, both of them collide each other, as you can see. It is because both of them have the property by default that the body is respondable. But what if I don't want the body to collide each other? Then I can use the characteristics of masking. When both of the body are separate, Then we use the concept of global respondable mask. When both of the body have a parent-child relationship, then we use the concept of local respondable mask. Here, as they are separate bodies, we will be using global respondable mask. For both the bodies not to collide each other, they should have alternative global respondable mask. Let's give alternative global respondable mask to both the bodies. Let's run the simulation. Let's move the cuboid towards the cylinder. Now you can see both of them does not collide each other. This is because the global mask of the cuboid and the cylinder cancel each other out. So now let's look into local respondable mask. Let's make the cylinder as a child of cuboid. To make cylinder as a child of cuboid, click cylinder, drag it and drop it in the cuboid. And now you can see a minus sign here. It indicates that cuboid is the parent and the cylinder is a child. So when there is a parent-child relationship, child can move, but the parent, when moves, it takes the child along with it. Now let's move a cylinder a bit towards cuboid. And now let's run the simulation. You will see both of them collide each other, even though they have alternative global respondable mask. So when there is a parent-child relationship, we'll have to use local respondable mask. Let's give an alternative respondable mask. Now let's run the simulation. You will see that both of them do not collide each other. Let's invert all the changes which we have made. And now obviously both of them collide each other. Now let's learn what are joints and force sensors. Two dynamic bodies cannot be connected using parent-child relationship just like this, because both of them being dynamic, they will act independently. So to connect a dynamic body with another dynamic body, VREP offers the features of joints and force sensors. If you want a rigid connection between two dynamic bodies, we use force sensors. To add force sensor, select add and you can see force sensor, and this is the force sensor. Let's move the cylinder a bit away from the cuboid and make it as often. Let's rotate the cylinder in relative to its own frame. And let's move it a bit towards. Now let's orient the force sensor along with the cylinder. Now the force sensor is inside the cylinder. Let's move both of them a bit more height. And the force sensor towards the cuboid. So now the force sensor is aligned properly between the cuboid and the cylinder. Now let's run the simulation. You still see that the cylinder just falls down and there is a sign along with the force sensor. It is because the force sensor is not joined with the cylinder. So there should be a parent-child relationship. So now let's make the cuboid as a parent of force sensor. So let's drag the force sensor and drop it in the cuboid. And let's make the cylinder as a child of force sensor. So now the cuboid is the parent and force sensor is a child of the cuboid and the cylinder is the child of the force sensor. Now let's run the simulation. You will see that the cylinder remains fixed in that position and it does not depend upon any irresponsible mass. What if we want to rotate this cylinder with respect to the cuboid? Then the VREP offers the features of joints. To add a joint, select joint, add revolute joint. Revolute joint is a joint which rotates its child relative to its parent. Let's bring to the same orientation as that of force sensor. But before that, let's change the parent-child relationship between cuboid and cylinder. Let's give the same orientation as that of force sensor to the revolute joint. Let's delete the force sensor. Now the revolute joint is aligned properly between the cuboid and the cylinder. And let's make the cuboid as a parent of the revolute joint and the cylinder as a child of the revolute joint, just as we did for force sensor. Now let's run the simulation. Now you'll see that still the child is not moving. To know about it, we'll have to look at the features of the revolute joint. Double click revolute joint and select show dynamic properties and select motor enabled. Now let's run the simulation. Now the motor is enabled. Let's give a target velocity while the simulation is still running. Let's give a 30 degree per second. Now you can see that the cylinder is rotating relative to the cuboid. So VREP offers the features for a revolute joint to give maximum torque as well as the target velocity. There is also features of enabling control loop and setting target position, just like a servo works. But representing a model using simple primitive shape is not good for the visual aspects. For instance, if this is a wheel, we cannot represent, it's not trivial to express the wheel as a simple cylinder. To add visual aspect for it, VREP offers the features to add meshed files into the scene. Mesh files or STL files or OBJ or DXF are the files which are created from designing softwares like SolidWorks or Fusion 360. Let's add an STL file. To import an STL file, click File and Import and select Mesh. Let's select outer wheel, which is been saved in the scene already. Select OK. Now you can see an STL file and you can see the shape of it. This shape is called symbol random shape and it represents any mesh, and it has only one set of features and one set of visual attributes. If you see the orientation, it is a bit reoriented from the world frame. To reorient it to the world frame, select Edit, Reorient Bounding Box with reference to the frame of world. Now you can see it, the orientation of the imported wheel is well oriented with the frame. Now let's move the wheel towards the cylinder. Now you can see that both of them are aligned properly. But to show the visual aspect, the cylinder, the dynamic part, has to be made as invisible. To make it as invisible, in the scene object properties, as we have done before, let's make it invisible. So now the cylinder is invisible and it can be represented by a wheel. But for the wheel to act same as that of its dynamic part, the wheel has to be made its child of cylinder. So let's drop the STL imported into the cylinder and let's rename them. Now let's run the simulation and let's give a velocity to the motor. Now you can see that it seems as if the wheel visible is rotating along with the revolute joint. As the wheel visible has non-respondable and non-dynamic feature, it reflects the behavior of the wheel dynamic. But now the visual attributes make it easier. Let's give a different color for the wheel visible. To change the color, select Adjust Color, Ambient Difference component and give the color which you want. Let's give 0.28 in all the RGB sector. Now it's look like black, which is soothing for our eyes. Now let's add something to fit inside the wheel. Let's reorient with the world frame. Let's give better color to it. And let's make the orientation of them proper. As both of them can be made together, let's group them together. Select both of them, right click, select group merging and select group selected shapes. Now both of them becomes the same shape. Let's make it as a child of the wheel dynamic. And let's rename it. Now let's run the simulation. Let's give a 60 degree per second. Now you can see that the wheel is rotating and the visual attributes also look good. So these are the features of joints and force sensors. Now let's look into our model. Let's clear the scene. As you have already installed collector.ttm, you will find that in mobile folder, click it, drag it to the scene and drop it. So this is our model, and you can see various shapes as we have already studied here. There are primitive shapes, there are simple random shapes, there are compound shapes, and you can see the visible paths which you see right now, and behind it dynamic paths and force sensors and revolute joints. To run the simulation, press start button. So the dynamic response calculations is being made in the dynamic paths, and the visible paths is used for are made as collidable and used for collision response calculations and for visual attributes. So we have learned the object properties in VREP, joints, force sensor, and we have seen and got familiar with the collector bot model. Good luck guys.